In the realm of sequential decision-making agents, a significant challenge arises when dealing with long-horizon tasks that necessitate multi-step reasoning. To address this issue, various reinforcement learning algorithms have been developed, focusing on improving credit assignment, introducing memory capabilities, altering the agent's intrinsic motivation, or its worldview. This research hypothesizes that exploration and representation learning can be enhanced by separately learning two different models from a single offline dataset. The authors focus on the NetHack benchmark, a challenging terminal-based roguelike video game that requires completing multiple subtasks to win. Human players struggle to fully solve the game, with only around 1% achieving success. Undirected exploration is intractable in this scenario, as the agent must try an exponential number of actions in trajectory length. Recent works have shown that even powerful exploration techniques, such as R&D, do not make significant progress on harder tasks within the NetHack learning environment. The authors propose addressing this problem by determining the action expansion order through either modifying the agent's intrinsic motivation or structuring its internal world representation. This research explores the idea of leveraging representation learning to achieve more sample-efficient exploration in long-horizon RL problems. By amortizing the sample complexity of representation learning by pre-training the agent on offline data, an approach that has led to advances in complex, multimodal control tasks such as Minecraft, the authors test their hypothesis in the NetHack learning environment. This challenging domain features high-dimensional state and action spaces, a strong notion of forward progress, and an organic definition of multiple subgoal tasks. The aim is to investigate whether combining representation learning with exploration improves performance on long-horizon tasks. Accelerating exploration and representation learning through offline pre-training is crucial in complex domains like NetHack, where symbolic agents and humans outperform reinforcement learning (RL) agents. The NeurIPS 21 challenge highlights the performance gap between RL agents and humans. Previous work, Explore like Exports, ELE, demonstrated that sparse reward tasks can be solved by learning a simple scalar function that predicts expert progress or temporal distance between two observations. However, ELE discards useful information in expert trajectories by compressing the dataset into a single scalar-valued function, which hinders its performance on dense reward tasks. This work addresses these limitations by utilizing the same expert data to learn representations through contrastive pre-training, achieving better sample efficiency and performance than ELE and standard imitation learning baselines. Specifically, a simple offline pre-training scheme based on contrastive learning can be used in conjunction with ELE, learning a progress reward on the same expert data. This improves the sample efficiency and base performance of Muesli, a strong RL baseline, on a wide range of tasks in NetHack. Auxiliary learning objectives, such as disentanglement, alignment, and predictivity of future observations, can equip RL agents with desirable inductive biases. World models provide a natural pre-training objective for RL agents, capturing crucial environment parameters. Single-step world models, like Dreamer v3 and Director, equip RL agents with single-step transition and reward models, while infinite horizon models, like models and contrastive value functions, directly capture the probability of observing a future state. Exploration methods, such as count-based exploration, knowledge gathering, and curiosity, have been actively researched, and learning from demonstrations, including classical imitation learning methods like behavior cloning, Gale, and generative approaches like Form, can accelerate learning in complex domains. These methods have been extended to work with expert trajectories without actions and have been applied to various domains. In reinforcement learning, exploration and representation learning are critical challenges. Existing methods often rely on human expert annotations or complex reinforcement learning agents, limiting their applicability. To address these limitations, a novel approach is proposed, leveraging offline data without actions to guide reinforcement learning agents. The framework consists of an offline pre-training phase, where the agent's representations and progress model are trained on offline data, followed by an online fine-tuning phase. Unlike existing methods, such as ELE, which reduce the pre-training dataset to a single scalar-valued function, the proposed approach uses a more comprehensive representation of the data. In the reinforcement learning setting, a Markov decision process, MDP, is defined by a tuple M equals S, S0, A, T, R, gamma. The state value function V pi, S, is the cumulative per time step discounted rewards collected by policy pi over an episode of length h. The state action value function Q pi, S, A, is the expected return when taking action in state S and following policy pi. The reinforcement learning problem is to find a Markovian policy pi that maximizes the state value function over the set of initial states. Decomposing the value function as the expectation of the reward over the geometric mixture of case step forward transition probabilities allows the learner to handle delayed rewards, where only states are accessible. This approach is particularly useful in scenarios with delayed rewards. By leveraging offline data without actions, the proposed framework accelerates exploration and representation learning. Unlike existing methods, it does not require human expert annotations or complex RL agents, making it more applicable in real-world scenarios. The authors highlight the potential benefits of their approach, including improved exploration and representation learning capabilities. In the context of accelerating exploration and representation learning in long-horizon problems with large action spaces and sparse rewards, two key concepts are introduced. The explore-like experts, ELE, algorithm and contrastive representation learning. The ELE algorithm utilizes a pre-trained progress model to guide exploration by evaluating the progress in the task through a monotonically increasing function of states. This function is learned from optimal data, where progress is maximal. The second concept, contrastive representation learning, estimates the conditional probability distribution of future states given the current state using an implicit model trained via contrastive learning on offline demonstrations. This model approximates the future state visitation probability under the optimal policy. Both ELE and contrastive representation learning are employed in the Muesli baseline to enhance the sample efficiency of the agent during the online phase. This approach facilitates more effective exploration and better representation learning in complex environments, ultimately leading to improved performance in tasks with large action spaces and sparse rewards. A novel methodology integrating representation learning with exploration is proposed to enhance the sample complexity of an agent. This approach combines offline pre-training and online learning, leveraging contrastive pre-training for state representations. To evaluate its effectiveness, experiments compare the performance of tabula rasa Muesli and ELE with their counterparts employing pre-trained state representations. Baselines GAIFO, BCO, and form are also considered for comparison. The experimental setup involves 7 tasks from NetHack, ranging from dense to sparse rewards, including Score, Scout, Depth N, Level N, and Oracle. These tasks vary in sparsity, allowing for a comprehensive evaluation of the methodology. The now top 10 dataset, comprising human games from top 10 players on nethack.alt.org, is utilized for pre-training contrastive representations. This dataset provides a balance of trajectory quality and diversity, containing approximately 16K trajectories of expert play and 184M transitions. The frame budget for the experiments is set at 200M actor steps, inspired by the Atari benchmark, with the exception of the Oracle task, which requires a larger budget of 500M actor steps due to its harder exploration challenge. Contrastive pre-training of state representations is motivated by 2 key benefits. It simplifies the task for Muesli by enabling linear value function prediction, and it has been shown to outperform latent space or reconstruction-based objectives. The authors investigate the effectiveness of offline pre-training in accelerating exploration and representation learning in the NetHack learning environment. This environment generates complex observations, as showcased in Figure 2, which presents examples of tasks that require efficient exploration and representation learning. The authors compare the Muesli framework to ELE, with and without pre-trained state representations. The results in Figure 3 demonstrate that contrastive pre-training significantly improves the sample efficiency of both Muesli and ELE in dense reward tasks, such as Score and Scout. Moreover, contrastive pre-training enhances ELE's performance in sparse reward tasks, like Depth 2 and Level 2, by improving sample efficiency. The architecture employed consists of a residual network, ResNet, that encodes 80 by 24 TTY arrays into a series of 2D convolutional blocks. This ResNet encoder serves as the basis for contrastive pretraining, ELE's progress model, and the Muesli agent. During the online phase, the generated representation is passed through a recurrent network, LSTM, and a multi-layer perceptron, MLP, to predict policy and value heads in Muesli. In contrastive pretraining, the ResNet encoder is followed by an MLP to project state features into a latent space. ELE's progress model fuses two input states, which are then passed through a similar ResNet followed by an MLP to predict a scalar value in logarithmic space, corresponding to the temporal distance between the input states. The experimental results, ran with 5 random seeds and plotted with 1 standard deviation, demonstrate that equipping strong RL algorithms like Muesli and ELE with human demonstrations via offline pretraining significantly improves the sample complexity of the underlying method. While ELE outperforms Muesli on sparse tasks, the performance does not improve on dense tasks. However, using contrastive pretraining with both Muesli and ELE significantly improves its performance in the sample regime under investigation. Figure 4 presents a comprehensive evaluation of the proposed method, ELE, with pre-trained representation, in comparison to standard imitation learning baselines, including BCO, GAIFO, and FORM. The results demonstrate that ELE with pre-trained representation outperforms all baselines on both sparse and dense tasks. The episode returns are reported over 5 random seeds, with 1 standard deviation, showcasing the robustness of the proposed approach. The figure highlights the performance of ELE on various tasks, including score, dense, scout, dense, depth 2, sparse, depth 4, sparse, level 2, sparse, level 4, sparse, and oracle, sparse. The results indicate that ELE with pre-trained representation achieves superior performance on all tasks, especially in the low sample regime. Figure 5 further investigates the effectiveness of the encoder extracted from ELE, which is separately trained by contrastive pretraining. The results demonstrate that training a separate encoder by contrastive pretraining is more useful on all tasks, illustrating that ELE and contrastive pretraining capture 2 different dimensions of exploration and representation learning. The analysis reveals that pre-training with ELE significantly improves performance on tasks such as depth 4, level 2, level 4, and oracle, particularly in the low sample regime. Notably, contrastive pre-training without an exploration bonus struggles to solve the sparser tasks, emphasizing the importance of the progress reward. This finding suggests that the same dataset can be used for both pre-training representations and learning and exploration reward, targeting orthogonal problems. Exploration bonuses facilitate discovery of the reward, while representation learning enhances the agent's ability to exploit it. The results presented in figures 4 and 5 collectively demonstrate the effectiveness of the proposed approach, ELE, in accelerating exploration and representation learning with offline pre-training. The findings highlight the importance of pre-training representations and exploration bonuses in improving performance on various tasks, especially in the low sample regime. The evaluation of ELE plus pre-training is compared to standard imitation learning baselines, including GALE from observations, GAIFO, behavior cloning from observations, BCO, and FORM. The results, presented in Figure 4, demonstrate that ELE plus pre-training significantly improves convergence speed on sparse tasks, with only ELE and ELE plus pre-training able to solve them. On dense tasks, such as score and scout, many baselines learn the tasks, but contrastive pre-training significantly improves sample efficiency. An ablation study investigates the effectiveness of using the progress model's representation encoder as an alternative to contrastive pre-training. The results, shown in Figure 5, indicate that using the progress model's torso as an encoder takes off faster but eventually achieves poor performance compared to ELE with contrastive pre-training encoder. This suggests that the benefits of contrastive pre-training cannot be replicated by using the progress model's representation encoder. Another ablation study examines the effect of freezing pre-trained state representations during the online phase. The results, presented in Figure 6, show no significant difference in most tasks with or without freezing representations. This leads to the adoption of freezing representations as the default setting throughout the paper. The impact of encoder architecture on performance is also investigated. The study compares the performance of ResNet and Vision Transformer (VIT) models on state prediction accuracy. The results, shown in Figure 7, indicate that ResNet-like models are better suited for NLE, achieving higher training set and test set categorical accuracy compared to VITs. The discussion highlights the key findings of the paper, which demonstrate that pre-training state representations using contrastive learning and then using this network to initialize the representations provides a large sample efficiency improvement. However, pre-training alone fails to solve sparse tasks, and the addition of a learned auxiliary reward is necessary to aid exploration. The results validate the hypothesis that pre-training helps in representation learning and auxiliary reward aids exploration in the challenging NetHack environment. The equations and algorithms underlying the experiments are not explicitly stated on this page, but the mathematical concepts and methodologies are implicit in the discussion of contrastive learning, representation learning, and imitation learning. The page assumes a high level of technical expertise in machine learning and deep learning, and the terminology and notation used are domain-specific and precise. This page provides a detailed compilation of key research findings, methodologies, and significant advancements in the field of computational biology. The content is structured to ensure clarity and precision for both novice and experienced researchers, providing an accessible platform for understanding complex concepts and cutting-edge techniques. The list begins with a thorough exploration of bioinformatics tools and algorithms, which are essential in analyzing genomic data. These tools enable researchers to identify patterns, predict gene functions, and understand evolutionary relationships among organisms. Next, the page delves into the realm of systems biology, where mathematical models are used to simulate biological processes. This interdisciplinary approach allows researchers to understand how different components of a biological system interact and respond to various stimuli. In addition, the page discusses the role of machine learning in computational biology. By applying machine learning algorithms to large datasets, researchers can predict protein structures, identify potential drug targets, and even forecast the emergence of new diseases. Moreover, the page touches upon the importance of computational models in understanding the behavior of complex biological systems. These models help researchers simulate experiments, test hypotheses, and make predictions about future outcomes, thereby reducing the need for costly and time-consuming laboratory experiments. Finally, the page concludes with a discussion on the challenges and limitations faced by computational biologists. These include dealing with noisy or incomplete data, managing high-dimensional datasets, and ensuring the reproducibility of results. Throughout the page, technical terms and concepts are explained clearly, making the content accessible to readers from diverse backgrounds. The text also highlights novel ideas, significant findings, and important arguments presented in the original research papers, providing a comprehensive overview of the current state of the field. Reinforcement learning, representation learning, and exploration are interconnected fields that have witnessed significant advancements in recent years. The work of Ho and Ehrman, 2016, on generative adversarial imitation learning laid the groundwork for learning from demonstrations without explicit reward signals. This framework has been instrumental in shaping the development of reinforcement learning. Building upon this foundation, subsequent studies have made substantial contributions to the field. For instance, the use of deep neural networks in reinforcement learning has enabled the learning of complex policies and value functions. The incorporation of auxiliary tasks, such as representation learning, has further improved the efficiency and adaptability of reinforcement learning algorithms. In the realm of representation learning, researchers have explored various techniques, including contrastive learning and generative modeling. These approaches have been shown to facilitate the learning of robust and transferable representations, which are essential for effective reinforcement learning. Moreover, the incorporation of exploration strategies, such as curiosity-driven exploration and count-based exploration, has enabled agents to navigate complex environments more efficiently. Notably, the work of Lillicrap et al. 2015 on deep deterministic policy gradients has demonstrated the potential of model-free reinforcement learning algorithms. Similarly, the development of proximal policy optimization by Schulman et al. 2017 has introduced a model-free, on-policy reinforcement learning algorithm that can efficiently learn complex policies. The integration of reinforcement learning, representation learning, and exploration has led to the development of more sophisticated algorithms, capable of tackling complex tasks. However, challenges persist, including the need for more efficient exploration strategies and the development of more robust and generalizable representations. Future research directions may involve the incorporation of additional modalities, such as language and vision, to further enhance the capabilities of reinforcement learning agents. Reinforcement learning, exploration, and representation learning are key areas of focus in recent research papers. Offline pre-training has emerged as a promising approach to accelerate learning and improve performance in sequential decision-making tasks. Yang and Nahum, 2021, demonstrate the importance of representation learning in offline pre-training, showcasing the transferability of learned representations to new tasks. This leads to improved overall performance, highlighting the significance of representation learning in reinforcement learning. Prototypical representations in reinforcement learning, as proposed by Yaritz et al. 2021, offer improved exploration and learning efficiency. Conversely, MetaCure, a Mater enforcement learning framework introduced by Zhang et al. 2021, leverages empowerment-driven exploration to adapt to new tasks. This work underscores the importance of exploration strategies in Mater enforcement learning. Behavioral cloning and generative adversarial imitation from observation, explored by Tarabi et al. 2018a, 2018b, involve learning from expert demonstrations. Vinyals et al. 2019 demonstrate the application of multi-agent reinforcement learning in achieving Grandmaster-level performance in StarCraft II. This work showcases the potential of reinforcement learning in complex decision-making tasks. Furthermore, Wang and Azola, 2020, investigate the theoretical foundations of contrastive representation learning, focusing on alignment and uniformity on the hypersphere. This work highlights the importance of representation learning in reinforcement learning and the potential benefits of leveraging contrastive methods. Prototypical representations, empowerment-driven exploration, and contrastive representation learning are key concepts that have been explored using equations, algorithms, and mathematical frameworks. For instance, the utility of prototypical representations is demonstrated through the derivation of novel loss functions and exploration strategies. Empowerment-driven exploration is formalized using probabilistic graphical models and variational inference. Theoretical foundations of contrastive representation learning are established using techniques from differential geometry and information theory. Collectively, these papers provide insights into the interplay between exploration, representation learning, and reinforcement learning, emphasizing the need for developing efficient and effective learning strategies in complex decision-making tasks. Key findings include the transferability of learned representations, the benefits of prototypical representations, and the significance of exploration strategies in Mater enforcement learning. Limitations of the current approaches include the need for large datasets, high computational requirements, and the challenges of learning from expert demonstrations. Future work includes exploring the application of contrastive representation learning in reinforcement learning and developing more efficient exploration strategies. The appendix provides supplementary experimental details and results, including the distribution of offsets between current and future states, denoted as T. A truncated geometric distribution, T-geom-T1, is employed, offering discrete support for direct sampling of time offsets without truncation and an extra parameter that can be tied to the environment, enhancing flexibility. In contrast, ELE uses a log-uniform distribution, T-log-uniform, T-H. Figure 8 compares these distributions, showing coincidence for certain success probabilities. The computational resources used in the experiments are specified as 8v100 GPS for 6 hours. Additional results are presented, such as the performance difference between using a frozen pre-trained state representation in the online phase versus allowing the gradient of the online loss to propagate through the representation, as depicted in Figure 9. The algorithm pseudocode for pre-training with online learning is provided in Algorithm 1. The input consists of a dataset DPO, H, environment M, state embedding, and policy. The algorithm first pre-trains the state representation using equation 11, and then learns the forward progress model, ELE, by minimizing equation 8. The online encoder is initialized with the pre-trained, and the trajectory is generated using the acting policy. The reward is updated by adding the progress reward, and the policy is updated using the muesli loss function while keeping frozen. Figure 9 presents a comprehensive evaluation of the proposed method, comparing episode returns with and without freezing contrastive pre-training representations during the online phase. The results indicate no significant performance difference for most tasks, suggesting that the pre-training phase effectively captures necessary information, allowing representations to be frozen without compromising performance. The proposed method's implementation details are outlined in A.4, with hyperparameters listed in Table 1, highlighting differences from the baseline method ELE. Notably, the contrastive discount rate is set to 0.95, and the batch size is 576 sequences, while all other hyperparameters remain identical to those used in ELE, and the encoder architecture remains unchanged. Experiments were conducted using 8 TPUV3 accelerators with a pod racer configuration, as described in Hessel et al. 2021b, enabling efficient and scalable computation. Results in Figure 9 are reported over 5 random seeds, with 1 standard deviation, providing a comprehensive understanding of the approach's performance, robustness, and reliability. The findings demonstrate that the proposed method can effectively leverage pre-training to accelerate exploration and representation learning, achieving competitive performance without requiring significant architectural modifications. The approach's ability to utilize both sparse and dense representations is also evaluated in Figure 9, with results showing strong performance across various representation types, including Depth 2 and Depth 4 sparse representations, as well as Level 2 and Level 4 sparse representations. The results and implementation details provide a thorough understanding of the approach and its evaluation, highlighting its effectiveness in accelerating exploration and representation learning, and its potential for applications in various domains.